All right, so we're going to talk about how to draw a free body diagram. A free body is an object that's going to have forces applied to it during a problem, a physics problem. So let's say that I have a box, and that box is sitting on some flat surface. Okay, and I want to draw the free body diagram for this box. Okay, so the first thing we want to do is draw an x and y axis. Okay, so I'm going to draw my x and y axis, and now we're going to talk about all the forces acting on the box. Okay, now there are two different kinds of forces. There's a contact force, which means it has to touch the object, and there's a non-contact force, which means it doesn't have to touch the object. All right, so what non-contact force is acting on that box right now? In other words, what's some force that's acting on it that's not having to touch the box? Okay, hopefully you said the force of gravity. So we're going to put our arrow pointing down because that's the direction that gravity points, always straight down. And to write our force of gravity, we're going to do a capital F and then a lowercase subscript g for gravity. And then make sure that we put our half arrow on top. That's the vector symbol because force is a vector. It has magnitude and direction. Okay, there are no other non-contact forces. Everything else that's acting on that box is acting on it because it's touching something. So the box is sitting on this surface, so it's touching that surface. The name of the force that comes from touching a surface is the normal force. Okay, it's capital F, then a capital N subscript. Now in physics, the word normal means perpendicular, okay? And perpendicular means right angle, okay? So when two things are perpendicular to each other, they are at right angles to each other. So our normal force here is perpendicular to the surface that the box is sitting on. Okay, a normal force will always be perpendicular to the surface the object is touching. All right. Okay, so that was one situation. Let's do another one. Let's say that maybe we're moving, okay, and we've got a truck and we're gonna start loading up some boxes into our moving truck, okay? And we're gonna use this ramp on the truck in order to move the box, okay? And we want to do a free body diagram for this situation. All right, so let's see here. Let's say that there's somebody that is pushing on that box. To try and make it go up the ramp, okay? And let's say that there is friction, okay? So there is friction between the ramp and the box, all right? So the first thing that we want to do is we want to draw our x and y axis. Now, I suggest that we kind of tilt our x and y axis and make it follow the ramp, okay? Now let's start putting all of our forces on there, okay? So is there a non-contact force acting on that box right now? Some force that doesn't have to touch it in order to act on it? Hopefully you said gravity. And gravity always acts straight down, okay? Even if you tilt the axis, gravity still acts straight down. All right? There are no other non-contact forces, so now let's think about contact forces, things that are touching the box. All right, well, the box is on that surface, it's on the ramp, so that means that it should have a normal force. So if there's a normal force, that's going to act perpendicular to the surface the box is sitting on, meaning 90 degrees. All right, so there's our normal force. It's 90 degrees from the surface that the box is sitting on. And then we've got this little guy over here pushing on the box. So that means there would be an applied force up the ramp. So that's going to be F sub lowercase a. And that's what we use for an applied force. That just means something's pushing on it. And then we said there was friction, right? There is definitely friction here. And friction always opposes the motion. So that means if the box is going up the ramp, then friction is going to point down the ramp. And friction is going to be our little fancy F, okay, a little F with a little curvy tail. And since the box is moving, this is going to be kinetic friction. So we're going to put a little subscript K there. And then don't forget our little vector half arrow above the force. Okay, so that's our second free body diagram. All right, let's do another one. Let's say that we've got, say maybe we've got a bucket of water, and say there's a string attached to that bucket of water, okay? And let's say that the string is pulling the bucket up at a constant velocity. Okay, it's moving it up, pulling it up at a constant velocity. Well, if it's moving at a constant velocity, then that means that its acceleration in the y-axis is 0 meters per second squared, okay? Now, put a little dot here for our free body, so I'm just kind of concentrating all the mass of the bucket and the water and everything in one location, right there at that center point. Okay, so I'm going to put my x and y axis on it, and now we can start listing all the forces that we have. So what's a non-contact force acting on that bucket and water? Force of gravity. Good. So we're going to draw the force of gravity acting straight down. Okay, now let's talk about contact forces. Is there anything touching that bucket? Yeah, the string up here. So we're going to have a tension force pulling on the bucket upward. Okay, a tension force. So we do a capital F and then a capital T as a subscript, and make sure we put our little vector symbol there. Okay, now since the acceleration is 0, like normally if it was just gravity acting on this, the acceleration would be negative 9.81 meters per second squared, because that's what little g is. Okay, but in this case it's 0. That's a number larger than negative 9.81, which means that the tension force here needs to be a bigger arrow than the gravity force. So the bucket is actually moving up. If the bucket weren't moving up, then the tension force arrow and the gravity arrow would be the same size. They would just be pointing in opposite directions. Okay, let's do another one. Let's say that we've got a ball, and let's say we dropped the ball, okay? And so the ball is falling down, and there is no air resistance. All right, so let's do our free body. So the first thing we want to do is make an X and Y axis, okay? I'm gonna represent that ball with a little dot. That's gonna be my free body, okay? So now I'm gonna put my X and Y axis here, and let's do all the forces acting on that ball. Okay, so are there any non-contact forces acting on the ball? Good, hopefully you said gravity, and that's pointing straight down. Are there any contact forces acting on the ball? In other words, is there anything touching the ball that's applying a force? No. So that means this is the free body diagram, just has force of gravity. All right, let's do another one. Let's say I've got a ball and I dropped it, and this time there is air resistance, okay? All right, so I'm gonna put another little dot here to represent my ball, and now let's do our X and Y axis, okay? Are there any non-contact forces acting on the ball? Yeah, so we've got the force of gravity, and that acts straight down. Now, air resistance. You can think of air resistance like friction, but in the y-axis, okay? So if the ball is falling down, which way would air resistance be acting? Okay, hopefully you said up, all right? So we would have air resistance pointing in this direction, upward. All right, let's do another one. Let's say that I've got a ceiling and I have hung a potted plant. So let's see, I've got my little pot here and there's my little plant. All right, so I want to do a free body diagram for that potted plant system, okay? So we're going to put a little dot here to represent the potted plant, and then there's one string, there's another string holding it up, okay? All right, so let's set up our X and Y axis, okay? And let's start putting forces on it. So, are there any non-contact forces acting on that? Yeah, so we've got gravity. Gravity is acting straight downward. Okay, now let's talk about contact forces. Is there anything touching the pot? Yeah, we got two strings. And remember, strings or rope, something like that, is going to have a tension force. But there's two of them, so we got to be careful with our labels. So we can call this one tension force 1, and we can call this one tension force 2. All right, let's do another one. Let's say that I have a ball and I've thrown the ball upward, okay? Let's do a free body diagram for it. So here's the free body. I'm going to set up my X and Y axis, and I want to start doing my forces. So, are there any non-contact forces acting on it? Yeah, gravity. Gravity's acting on it. Straight down. Okay, are there any contact forces? So this is after I've thrown the ball up, while it's on its way up. Is there anything touching it? No. So then that's it. That's our free body diagram for it. Okay. What if I have a ball and I have rolled that ball along a rough surface so that the ball is slowing down and coming to a stop? Okay, so it's coming to a stop. All right, we're going to put a little dot so it can be our free body. And then I'm going to do my X and Y axis. All right. Are there any non-contact forces acting on that ball? Yeah, we've got the force of gravity, and that always acts straight down. Okay, do we have any contact forces acting on the ball? Okay, so since the ball is touching a surface, we're going to get a normal force because of that surface. So the normal force is 90 degrees to the surface that the object is touching. All right, is there anything else? Hopefully you said friction. Okay, since that ball is coming to a stop, it's rolling over a rough surface and it's slowing down and coming to a stop, we're going to have friction. Okay, and that's going to be kinetic friction because the ball was already moving. Okay, and somebody, of course, initially had to push that ball to make it start moving, but we're not talking about the ball at the moment that it's pushed. We're talking about the ball after it's already rolling along the surface. So there's no other forces acting on that ball right now. All right, what if I have a large rock, okay? And I got somebody standing here and they are pushing on that rock, big giant boulder, okay? And it's not moving. Okay, they're pushing on it, but it's not moving, all right? And I want to draw the free body diagram for it. So we're going to put a little dot for our free body that represents the boulder. And I'm going to do my X and Y axis. All right, so let's come up with the forces. So is there any non-contact forces acting on that boulder right now? Hopefully you said gravity, so that's going to point straight down like it always does. Okay, now contact forces. All right, so it's sitting on a surface, so that means there's going to be a normal force. So hopefully you said that. And then we got this little dude here pushing on it to the right. So that means that there's going to be an applied force acting to the right. Are there any other forces? Yeah, he's pushing on it, but it's not moving. Something is preventing it from moving. And that's going to be friction, okay? But what kind of friction? Static friction, okay? So we're going to have static friction because the boulder isn't moving at all. So if something is already moving and it's slowing down, that's kinetic friction. If something's not moving, there's a force acting on it, but it's not moving yet, then it's static friction. Static friction is the amount of friction you have to overcome in order to get an object to move in the first place. And then once it starts moving, then kinetic friction is acting on it the whole time that it is moving. All right, well, this was just a quick video on how to draw some free body diagrams for various situations. Thanks for learning with me today. Bye.